reviewing some reactions here. We'll go back to this in a second. But let's look first at the outline for chapter 11. And, well, no, first let's do ChemTube a little bit. So here is ChemTube, the organic reaction animation. So this is a good one. This is the cis and the trans 2-butene bromination to give the two different products there. And let me see if I can get a little closer there. Maybe, yeah, okay. Yeah, you can go to that website, of course, and manipulate these things on your own. It's a great resource. Let me just click through a little bit here on ChemTube. You go to Electrophilic Alkene editions, and you can see these pretty well, I think. This is the reaction here with trans 2-butene with bromination. It shows you the bromonium ion formation. Maybe we can look at that. And then you see the animation there on the left. So here's the cyclic bromonium ion, right, that just formed there. And let's open up the bromonium ion. So we'll click on the next arrow there. And there you go. You see it open up. And it gives the what? The meso compound. This one, if you rotate around, you see the center of symmetry here in this one, and the plane of symmetry, which means the trans, upon bromination or chlorination, gives the achiral product there. And if you start with the cis alkene here, let's see. There you see the geometry changing now. The two methyls are cis to each other. And if you open up there, on either side, you get the chiral one, either the RR or the SS. And those are the chiral ones. Of course, you can play around with these controls and have it spin, get a better view of it, I think. And you can play a reaction backwards and forwards. Let's have that go. So there's the ring opening of the bromonium ion. It's going backwards there, and it's opening up. And let's have it spin it also, maybe, yeah. So that way you can see it. You can manipulate it with your mouse and see it on any device there. But I think that's a great resource for you there. Okay, let's go out of that and go to the outline here for chapter 11. So alkynes. And what do we need to know here? Well, it's just those same reactions. We're going to use those 5 reactions. Well, actually, we're going to leave out halohydrin. We're just going to do hydrohalogenation, halogenation, hydration, and hydroboration with alkynes. That's probably enough. We've already talked quite a bit about the structure. We'll review a little bit about that. Properties on their own, they're very nonpolar, not water soluble. But the pKa of a terminal acetylene, you see, is 25. So there's a lot of bases, sodium amide, sodium hydride, and other strong bases, not t-butoxide or hydroxide. Those aren't strong enough. The pKa, the conjugate acid there, is lower than 25. So you need amide or hydride to be able to deprotonate there. But that's the thing. I'll show you a couple compounds, mainly the birth control and the abortion pills that are based on alkynes. But alkynes are all over the place, just like alcohols and alkenes there. Preparation, E2 eliminations. So from dihalides with 2 equivalents of t-butoxide, we can do that. And then we can form the terminal acetylene anion and then do SN2 alkylations with it, with alkyl halides. Preparations there, reactions, electrophilic additions there, and then some synthesis reactions with the acetylene anions. So hydrohalogenation we'll do first. 1 equivalent of HCl or HBr will form the vinyl chloride or bromide. And that's the same thing. The electrophile here is the proton. We'll protonate there, flow the electrons, and then have the halide nucleophile add in there. And then you can do it again. You see you got another alkene here. So there's hydrohalogenation of the alkene. And we always put the second halide on the same carbon with the halide, okay? And that's due to resonance stabilization and the proton wanting to go away from the halide to give that resonance stabilization. So more substitute carbocation, and then the halide anion coming in. So we can halogenate the two equivalents of bromine or chlorine, form the dihalide. It's got an alkene there still. Remember, an alkyne has two pi bonds and a sigma bond. So the first additions here just add to the one pi bond. Then the second pi bond can be added to form what? The tetrahalide. So you have 4 chlorides or bromides here. Okay, hydration is also similar, but here is the new twist, and this is the most important concept, I think, of chapter 11. Once we do one hydration of a pi bond here on the alkyne, we'll get an alcohol, okay, just like before, sulfuric acid. Sometimes we add mercury sulfate with alkynes. It forms a mercurinium ion. You don't need to worry about that. In fact, mechanistically, I won't show that. We'll just use the acid here, attack with water, and you see, loss of the proton off the water, off the hydronium ion, will give an alcohol. But this is now a vinyl alcohol. That's a special name called an enol for alkene alcohol, right? Enols are tautomers, we say, of ketones, because you can just move this proton down here, put the pi bond now between carbon and oxygen, and move that proton all the way over here to this position, and that gives the ketone version of this enol. And I'll show you how those work. In most cases, the ketone or aldehyde carbon-oxygen pi bond is always more stable than having the pi bond between the two carbons in the alcohols. Vinyl alcohols in general are not stable. They'll readily tautomerize. There's that term, the new term there. Switch over to the more stable ketone version. Follows Markovnikov addition. Like we saw before, regioselectivity. So if it's a terminal alkyne, it'll form a ketone in the middle. There's a way to form aldehydes from acetylenes. If it's a terminal acetylene here, you see the alkynes on the end. We can hydroborate like before, and the electrophile goes on the N carbon, just like before. Then we oxidize this, you see, with the same reagents, peroxide base, to the enol form. And then the enol tautomerizes, you see, because the alcohol's on the N now, we get the aldehyde product. So there it is. And then we'll have the acetylene anion alkylations, reactions of the anion here. We can form that with strong enough base, sodium amide or sodium hydride, form the acetylene anion, negatively charged. That's a good nucleophile now, right? And with primary halides, we can then do SN2 chemistry to form new alkyne products. And we can also open up epoxides because it's a charged nucleophile. Always reacts at the less hindered carbon right here because it's SN2, right? And pop that open. See, they got the extra carbons added here. And then protonate with water or weak acid. You can also protonate with acetic acid or dilute hydrochloric or sulfuric acid. And that'll protonate the alkoxide anion, give the product there. And we'll do some synthesis and forward synthesis planning. I'll show you how to do some reactions there, but I think we're good for that. Let's refocus here and go up to the board and look at our reactions we're going to do here today to cover this chapter. Zoom out a little bit. Oh, we leave it a little bit there for you. Okay, that should be good. All right, so we have a review here of the 5 key reactions. What do we have? We have hydrohalogenation, and we have hydration here. We have halogenation, chlorine, and then we have bromohydrin, bromine and water, and then we have hydroboration. With what substrate? We're going to start with just one butene. So if you want to pause the video and try to come up with these products, go ahead. Get that erased. So let's see. What did you come up with? Well, this one will give what? The Markovnikov Bromide. Everybody okay with that product? So our electrophile in this case is the proton. It goes to the end. We have the secondary carbocation, and that's where the bromide attacks. So I'm not doing the mechanism right now. We'll review some of that when we talk about the acetylenes here in a second. What's our next one here? Hydration. Same thing with the strong acid. It'll be Markovnikov hydration. So the alcohol will be at the more substituted position. And then chlorination will form the dichloride. So we have two chlorines on there. It's the chloronium ion, and then opening it up. We can't see backside attack or anything there. And by the way, stereocenters are here, here, and here. These are all what? DL. Okay, so we can have attack top or bottom. You can keep track of that. And then we have halohydrin. So same thing, bromonium ion. And then water goes where? It goes at the internal position, because that's where most of the carbocation character will be on the bromonium ion, at the secondary position. So as the bromonium ion opens up, water attacks there, and then you lose the proton off water. So water is the nucleophile in that case. The electrophile is still bromine in that case. Then we have the opposite, anti-Markovnikov alcohol-forming reaction, hydroboration here. Boration, hydroboration. And what we're going to form is the less substituted alcohol, right? So the primary alcohol. So these two reactions we say are complementary, right? Hydration, more substitute alcohol, and then less substitute alcohol. All right, let's do another one here, alkene-wise. How about this alkene for all 5 of these reactions for a review here? 1-methylcyclohexene. Let me get these off. You want to pause your video there and try those. Let's see what products we get. All right, so same thing, Markovnikov Hydrohalogenation. So we're going to form what? The more substituted halide. Okay, so it'll be at the tertiary position. The proton will go here to give us what now? A tertiary carbocation. Same thing here for hydration. We'll get the alcohol. Now, what about the chirality here? These are all achiral, I think. Well, no, not here. Not from here on down. We'll have stereocenters. These two are achiral, the Markovnikov additions here. Chloride here. Now we've got to keep some stereochemistry relative. The two chlorides have to be what? Trans to each other, okay? And that's the chloronium ion, top or bottom, it doesn't matter, and then chloride anion attacking opposite, and that opens up the chloronium ion. So that'll be a DL pair. You can draw the enantiomer of that you'll also get your mechanism. You could practice to see that. Same thing here, halohydrin. We'll have alcohol down, bromide up. You should probably draw it like that, although this stereocenter would probably be a mix of diastereomers because it is tertiary at that point. As the bromonium ion opens up, water could go top or bottom. So this one will be kind of a mix. We give you full credit for either one, or if you didn't show the stereochemistry, but just showed the product. But make sure you have the bromide at the less substituted carbon and then the alcohol at the more substituted carbon. That's the key thing there. And what about hydroboration here? We'll have borane. Let's do the borane adding from the top face here. So it'll push the methyl group down. It'll have the hydrogen up. And initially the boron will be up. And then the oxidation here with peroxide and base will also go with the retention of that stereocenter. So that alcohol will also be up, okay? Notice the methyl and the alcohol are what? Trans to each other. And you see the hydrogen and the OH from the hydroboration are cis to each other. That's because of the syn addition here of the borane adding from the same face, okay? Which will give the hydrogen up and the borane up, which gets oxidized to that. So that's a good review, I think. Questions about that? Go back to the previous classes. Talk to us in recitation and office hours about that. But make sure you master these 5 key reactions because they carry over now in the alkynes. So let's see, alkynes. What do we need to do here? Well, let's do a little bit on structure maybe, and maybe preparation too a little bit. So alkynes, we change the prefix or the suffix part ane, we put a y in there, alkyne. And we have carbon, triple bonds. It's one of the functional groups we learned before. And what about hybridization? sp hybridized, right? So there's 2 pi bonds and a sigma bond right here for the triple bond, okay? And also, what about the distance here between the 2 carbons? Well, it's 1.21 angstroms. That's the shortest bond yet we've talked about. Why? Because there's 6 electrons now shared between the 2 positive carbon nuclei. That lets the bond distance shrink down there between those. So remember we had alkene was 1.34 angstroms, and a regular alkane carbon-carbon single bond is 1.54 angstroms. That's the longest bond, carbon-carbon bond. The carbon-hydrogen bonds or carbon-carbon bonds on this side also shrink down a little bit relative to sp2 and sp3 hybridized carbon. Yeah, I think that's all we need to do there. Let's do a little bit on naming now. They are nonpolar overall, although, sp hybridized carbons are a little more electronegative than sp2 or sp3, but not by much, not enough to make them polar enough to be highly soluble in water. In fact, if there's no other polar functional groups, alkynes, alkenes, alkanes are not soluble in water because they're generally non-polar bonds overall. Naming, so wherever the alkyne is, we have this number, this locant in the front, the number X, which refers to that position there. Alkynes have priority over halides and alkyl groups, so you give it the lowest possible position. But alcohols have priority over alkynes, and alkenes also have priority over alkynes. So I'll show you how to use that a little bit to figure out the names here. We'll be brief on names. It's not that big of a deal. So here we got this chloroalkyne here. Longest 1, 2, 3, 4, 5, 6, 7. So this is a heptyne. And that's always the first thing you do, right? The longest thing includes that. Make sure you count these 2 carbons. They're right there and there. Sometimes students leave those off. So at what point are we going to number in? 1, 2 for the chloride or 1, 2 for the alkyne? Yeah, it's there. Sometimes we put the number down here, and then a 2-ine or 2-ene or 2-ol. We have the number here. The book does that sometimes. I like to put it out front to identify the parent here. It doesn't matter. The IUPAC will accept both for that. So wherever you put it, I like to put it there. That's probably where you'll see it. And then what else do we have on here? 1, 2, 3, 4, 5, 6 chloro. Now, we're not defining stereochemistry, but of course we could do that, whether that's R or S, if it's a wedge or a dash, whatever. Let's just do it there. So you're pointing out that chloride gets the higher number here, and the 2 is the higher priority alkyne there. There are such compounds as enones, and these have an alkene and an alkyne in them, but the priority goes to the alkene if you're numbering those. There are also diines. Diines, alkadiene is how they're named, alka or alkaenine. Diines can be like, dienes, alkadienes that we talked about before. Sometimes you see those numbered. Here, let's combine one with an alcohol. We'll keep nomenclature simple. It's not that big of a deal. How about this one? So we've got alkyne there. And now let's have a solid alcohol. So this is alkyne all. product. And which one is it? 1, 2, 3, 4, 5, 6. So it's a hex ine, and then the all position here. And do we give this number 1 here for the alkyne or number 2 for the alcohol? Well, alcohols have priority, which means they get the lowest number possible, regardless of anything that's lower in priority. So it's an alkyne 2 all. So there you see putting the number at the end there. So we need a number here in the front for the alkyne, right? So it's 1, 2, 3, 4, 5. Hex ine 2 all. And we're not done yet. What else do we need to do? We have to put in the stereochemistry in the front here, and I think that's indeed the R. So that R needs to be in the front. If there's just one stereocenter, you don't have to number it. Multiple stereocenters, you have to put a number in front of the R or the S. But I think that's good for that. Okay. Yeah. Try to keep that to a minimum. How about preparations of alkynes? Let's see. We actually know a lot of reactions of how to prepare alkynes. We've learned this reaction before. Here's a geminal dichloride, and let's use 2 equivalents of potassium tbutoxide. 2 equivalents, right? We've got the hydrogens we can take off here or here. Now, by Zaitsev's rule, where should we take the hydrogens off? Yeah, here, the more internal position. After 1 coming off, we get this product. Okay, after 1, what type of reaction is this again? Yeah, E2. Tbutoxide is always E2. So pull the proton there, flow the electrons off. Yep, vinyl chloride there. But we got a second equivalent. We've got 2 equivalents. So we've got another proton there at that internal position. And yeah, that will give us 2-butyne product. Okay, so preparation, we know quite a bit about this. We can also do this. Here's a ethylene compound. There's a alkene right here between 2 benzene rings. Now let's treat that first with bromine. And what we're going to do is form what? We're going to form the dibromide. And let's have 1 bromide up, 1 bromide back. Okay. And that's an anti-addition there, bromonium ion, backside attack. So there's a little review of chapter 10 there. And then let's do 2 tbutoxides, 2 potassium tbutoxides. Well, here's a beta proton to this leaving group, and there's another hydrogen here, beta to that bromide. So the product in the end is this. I think you can do the 2 E2 eliminations to give that product. Now, there's another reaction with alkynes that we'll cover toward the end, but I like to show it right here. So we can take acetylene and treat it with sodium amide. Okay, this is the sodium salt of the base that comes from ammonia. So the pKa of ammonia is what? 38. It's very high. The pKa of a terminal acetylene is 25 because of the high S character of that sp hybridized carbon. So 1 equivalent of base here can convert the alkyne into the anion. Okay. And what's the conjugate acid in this case? So it's ammonia. Okay. And then we react this charged small nucleophile with a primary leaving group. And it really does have to be primary. That's the main electrophile. If it's a secondary or tertiary, the acetylene anions do a lot of elimination mainly because they are highly basic. The pK is 25. That's way outside that 5 to 15 range we talked about. But this can do that. And what do we get? We get the new pentine product. With the acetylene on there, we just formed this bond right here. So there's an introduction to the synthesis here with acetylene. So we can use acetylene or another terminal alkyne here. In fact, we could do this again. Let's react this again with more strong base. Okay, another equivalent. And then let's treat it with ethyl bromide. Okay. So what are we going to get now? We're going to get the alkyne The propyl was already on there from the source step, and now the ethyl can come on there. So you see, you can build up a lot of these alkynes because you can sequentially form the anion on either side if you start with acetylene, which is the simplest alkyne right there. By the way, this is Welder's gas. It's a gas molecule. We have to condense this in a cold flask and then treat it with a strong base for a few minutes and then put in the electrophile that we want. Okay, I think that's good. Let's get into the other reactions. What? Hydrohalogenation, halogenation, hydration, and hydroboration. And we'll go kind of quick through some of these reactions. They're very similar to the alkene reactions, so we don't need to spend too much time on them. Here's the general idea, right? We're going to have electrophiles, okay? And the electrophile is going to be attracted to the pi bonds there. And then our nucleophile will come in here, okay? Notice the flow of the electrons. And what we're going to wind up with is what? Electrophile and nucleophile. Just like before. It's the same thing with these H reactions, right? So let's see our first one. What are we going to do? Let's do hydrohalogenation first. So our first H reaction, hydrohalogenation. We've got HCl. Let's do this one first. So what do we have here? We have a proton, okay? And I said you could abbreviate the acid here on the mechanism. Now, if we just stop there, that might be a problem. Because if we pull these electrons out, what are we going to get? We're going to get, yeah, this carbon-hydrogen bond. But what about this carbon now? Oh, that's an sp2 carbocation. That's not good. That's not resonance stabilized, and that can be a problem. What actually occurs here is you have enough of these ionized molecules, because HCl can ionize into what? H plus and chloride minus. And it's actually thought to be a termolecular type reaction, where it's got to collide with the acid and the nucleophile at the same time. And you see, if you do that, what do you get? You get that directly. Okay? Now, that's really hard to do, to stop with just one equivalence there. Normally, there's excess here. So if you have another molecule of hydrochloric acid, we can protonate again, right? And what? We do Markovnikov Protonation, right? There's already one hydrogen on here, so we just added the second one right there. And what's this carbon now here after this second equivalent? Right, it's a carbocation. And notice it's the more substituted carbocation. In fact, we could use the lone pairs on chloride. They're not very good because chloride's very electronegative, but that could help stabilize this more substituted carbocation. If you put the proton here next to the chloride, that would be a secondary carbocation. This one's tertiary, right? And then what do you have? Chloride minus attack. And yeah, that goes to the geminal dihalide, okay? Same thing for HCl, HBr also works in a similar manner there. If these are different groups here on the end, this is a symmetrical alkyne. You've got some differences there. In fact, let's look at a terminal alkyne. So let's do the same reaction, but with terminal. So let's say we've got, a propyl out here maybe, okay? So HCl. So what are we going to do? Well, our chloride here is going to come in at the more substituted spot. We're going to end up what with the proton on the end and the chloride there. Well, let's draw it like that. Okay, so the internal thing, and then more HCl. You see, we're going to put it on the end again, and then chloride will go there. And so we'll end up with this methyl on the end here. So two new hydrogens on the end there, and it's this internal geminal dihalide that's formed. Don't form the gem dihalide on the end carbon here, because that would be anti-Markovnikov. All right, let's look at halogenation. We got chlorine and bromine, and let's see what we need to do there. We've got chlorine with an alkyne here. And the first thing we're going to go to is this. Okay. And you could imagine chloronium ion, which would look something like this, right? It's a little more strained now, a little less reactive there. And then chloride has to come in here and go. It's probably more of a termolecular type process where all these things are colliding at the same time to go directly to that. This is not a great mechanism for that because this is sp2 hybridized and this is hindered now, this approach, this backside approach. So this termolecular thing where the electrophile and the nucleophile are attacking the alkyne simultaneously is probably better. Then you can do the same thing here with a second equivalent. And normally we do have excess on a quiz or test. We put a 2 out there, at least show you there's excess, okay? If it is one equivalent, we're stating it as such, then you do stop at the di one. But here you go on to the dichloro product. Okay. Yeah. And that holds for bromine as well, with terminal or internal ones. Okay, let's do hydration. And this is the one that has the enol and the tautomerization idea going on. So let's do the simple one first. With just 2-butene. And what are our reagents here? Yeah, sulfuric acid. And if we leave that out, no reaction occurs. Sulfuric acid and water, okay? And what are we going to go to? We're going to go to the ketone. And that's something new, it kind of looks like, right? Because before, what did we talk about? We talked about protonating here, right? And we're going to do that. We're going to protonate. And at the same time, we're going to add water in here because we don't want to have a vinyl or an sp2 carbocation intermediate. If we do this, what's the result? We'll get this. Hydronium ion and what? There's our proton. That proton right there came from the acid, right? So we'll get this. And then we have to use water to take off the proton there. And that will then generate what? Our enol. Okay? And that's like before, where we had an alcohol, but we didn't have an alkene there, right? We got the 2 pi bonds now. We've got the enol thing going on here. So what can we do now? Well, we're in the presence of acid. So let's put another acid on here. Now, if we do that, what happens? Look, we get that second proton there, alcohol there, and a carbocation right there. We just did Markovnikov Protonation to give the more substituted carbocation. And notice we have a lone pair here on the alcohol that can come down. In fact, this is actually a resonance structure where we can just bring those electrons down and form this, right? We're just moving this pair of electrons down to neutralize the carbocation right now. And now you need a plus charge right there. Okay. And then how do we form the ketone product? Well, we take another molecule of water. And yeah, this is more complicated mechanism. So you should examine that carefully and go over that. Let's see, let's review. So we protonate, put a proton on there from the sulfuric acid. That's right here. Okay, those electrons are pulled out. That will form a positive charge here that's captured by water. Okay. This is the hydronium of the vinyl group, the other pi bond that's left behind there. Take a proton off, not both of them, just take the one off for the hydronium ion. That'll give the neutral enol now, okay, the alkene alcohol, which is the different thing now. And then we can protonate again out here. There's another proton going on for more acid. That'll give a carbocation there, flow the electrons down. There's the pi bond now between the oxygen and carbon. Then take the proton off, which is originally on that alcohol, and then voila, there is the ketone product. Let's look a little bit more closely at this enol idea. In fact, let me redraw that enol. And if we look at that a little more detail, we can see a few things there now. So let's see. You know, alcohols, we've said before, are very stable. But again, this enol is sp2 hybridized here, okay? And in the presence of acid, you can protonate, right, and bring the electrons down and go to the ketone. Examining that, though, let's see, do we need to have acid to do this? In fact, enols, we can say, are in equilibrium with the ketone version, or the keto version, okay? This equilibrium depends on the type of carbon, but if we've got a carbon-oxygen pi bond, it's actually preferred to be in the keto direction, okay? Now, why is that? Well, we've got carbon-oxygen pi bond. Oxygen's more electronegative, and that actually is a stabilizing effect for the resonance of a carbonyl. We've drawn the resonance before of carbonyls. Can push the electrons out temporarily, have a carbocation here to negatively charge oxygen. Oxygen being more electronegative, you can flow it that way. But here you've got carbon-carbon pi bond between the two relatively non-polar groups there. So it's a little bit different there, but this equilibrium here can be adjusted whenever you form an enol as an intermediate or a product. It will normally equilibrate over instantly to the ketone, very fast thing, which just involves transfer of protons. And you can do it directly off of water here. So here I'm showing you how you can flow the electrons around the ring there. If water collides with an enol, it actually goes directly to this. And you can see you reform water just right up there. So here's the water that results from that. You're just shuttling the proton from the oxygen position down to this position. Again, those are called tautomers. Okay. Very important structures we'll see in a number of biological molecules. In fact, the base pairs in DNA and RNA have this enol keto tautomerization. In fact, here's an interesting one. Let's look at this enol. Now, you've seen this molecule before. What have we called it? Phenol, right? And you can focus on this part right here. And indeed, that's an enol, isn't it? On the ring here. Now, this is a benzene ring. It has some extra stability. But let's draw the keto version of that. It would look like this, right? Where we switch this hydrogen down to here, and now we have a methylene right there, right? So which is more favored, the enol version or the keto version of phenol? Well, it highly favors the enol. We'll learn later on that this is due to resonance stabilization there, okay? But indeed, this is an alcohol on an sp2 hybridized carbon where the enol is actually more stable due to aromatic resonance here, which is more than the carbonyl resonance that you normally get from simple enols, okay? So stay tuned for that, but you should be able to identify enol and keto versions by simply moving the hydrogen off of oxygen down onto carbon, okay? There's a couple ways to do that mechanistically, but I think that's all we need to say there. Let's look at hydroboration, which is the last one we're going to do. We're not going to do halohydrins. Those actually are reactions you can do with water and bromine or chlorine with alkynes. They give chloro or bromo ketone products, but it's not in your book, so I won't go over it. But let's look at this one. How about hydroboration? So we'll treat with borane first, and then peroxide base. Okay. So this similar thing, right? Here is our electrophile now. We're going to put it on the end, and hydrogen will go in the internal position, and it'll form that. Okay. So we always put the electrophile on the end carbon. So this is anti-Markovnikov addition, but according to modern theory and mechanistic understanding, the electrophile always goes down the end because the positive charge building up internally is more stable. So there's our hydride that came off the borane. Now we have the neutral borane. Now let's go ahead and do the oxidation now with the peroxide and the base. Remember that just converts the borane to the alcohol. Oh, well, there's another enol. Okay. That's not the product, though. What is the product? You need to tautomerize now, right? Put the proton on this carbon here at the 2 position and form what? The pi bond right there. Now we can do it with water. Let's see. I think we can just grab the proton off there, the electrons there, and move the electrons there. Okay, so I'm showing you the mechanism of just isomerizing with just regular water. You see it puts that other one there, and what happens to this carbon on the end? Ah, there's still a hydrogen here, right? Maybe we need to colorize these a little better. Here's a green one. This is one that's here, right? Okay. And which one did we just move here off of here? Okay. Yeah. That one is going to end up on water. And then that, yeah, this one here just ended up there. And so what do we have? Oh, there they are. Okay. Look at that. Color coding. The magic of the whiteboard, I guess. Okay. So what do we have now? We have an aldehyde product. And this is specific to hydroboration of a terminal alkyne. And what do I mean by terminal? It's at the 1,2 position. It's on the end. Now, if you hydroborate a terminal alkyne, you get this magic new functional group, aldehydes. That's one of the functional groups we had you remember. It's a carbon-oxygen carbonyl, like a ketone, but if it has a hydrogen on the side of the carbonyl, this is what? An aldehyde now. Aldehydes will be very important in biology. We'll see them in metabolism and in sugars and a number of places. But aldehydes are carbonyls on the end of thing here, okay? But terminal alkynes do that. Hydroboration, the same thing we learned about with alkenes in chapter 10, right? We've got the alcohol at the end here, and then that can tautomerize to give the aldehyde product. So hopefully you can see that. Let's do a couple of complementary reactions here just to illustrate this point. I think it's a good one. How about this alkyne? Cyclohexyl alkyne. You don't need to know how to name that. Let's see. Let's do it first with just hydration and water and acid. And then let's do it with hydroboration with peroxide and sodium hydroxide. So if you want to pause there, see if you can come up with the 2 products. Okay. Yeah. So if we hydrate it under acidic conditions, we're going to generate the ketone. Okay. So the ketone would arise from what? Protonation, then water attacking, and then tautomerizing to that product right there. If we hydroborate, we're going to put the boron on the end, and then we tautomerize, and what product are we going to end up with here? Yeah, not the ketone. Remember, a ketone has 2 carbon groups on the carbonyl. This has a carbon group, but it has the hydrogen there, so that's your what? Aldehyde. Okay, so make sure you can differentiate this 2 and apply these 2 reactions differently. Terminal alkyne, that's the general thing. If it was an internal alkyne, both of these reactions would go to ketones, okay? It wouldn't matter there because you have the methyls on the end, okay? And yeah, hydroboration will work with internal alkynes, but the cheaper one would just be hydration. It's when you have a terminal alkyne, you want to form the more valuable aldehyde in that case. Okay, let's see. Let's get into some acetylene anion reactions. And we've done some of these before, but I think we can look at a couple of these, and then we'll review a bunch of synthesis reactions along with sample test 3 on Wednesday. Sorry, yeah, the day that the exam's already starting, but in the morning you'll be able to watch the video and review for test 3 there on Wednesday. But so here we got some acetylene reactions. Let's do this. So let's react it with sodium amide. Oop. Okay, no. Oh, sorry. Whiteboard skills failing me. 2 there, okay. Yeah, there we got it. Okay, that will form what? The terminal acetylene anion. And then what do you want to react with? Let's react it with this bromide. Yeah, it's a primary bromide. And so what are we going to get there? We'll get the acetylene now at the internal position and this isobutyl group on that position. Okay. Now, if we did the hydration or the hydroboration of this internal, we get a mixture of different ketones at that spot because the 2 alkyl groups are different now. Let's take this same thing here, though, and react it with this epoxide. So what are we going to get there? Where are we going to attack this epoxide? At the primary position or the secondary position? Yeah, at the primary position. So that will give us this. Oops. Didn't want that. Sorry. Wanted that. Okay. Now, yeah, think about it mechanistically. So what are we doing there? We're opening up there. There was that primary spot, and there's 3 carbons, 1, 2, 3, right? And as we open up the epoxide, we just made that bond right there. We get this alkoxide. Now we've got to react it with water in a second step to protonate our product. You see, that will give us this alcohol product then. Okay. And those are very useful reactions, both alkylations, we call these, and this is, of course, epoxide opening. Make sure you work some of those problems and can see how some of those work. And we'll probably leave it there. Yeah, I think we're out of time. We'll leave it there, and we'll